Let's imagine that we have a mass of 15 kilograms resting on a horizontal surface. There is a coefficient of kinetic friction, mu sub k, of 0.150 between the block or the object and the surface, and a coefficient of static friction of 0.200. Let me just point out one thing. Notice that mu k is less than mu s. That is always going to be the case. Mu k is always less than mu s. In other words, the kinetic frictional force, mu k times the normal force, is always less than the value of the maximum static frictional force, Fs max, which is mu s times the normal force. You have probably experienced this. Have you ever tried to push something and noticed that it's harder to get it started moving than it is to keep it moving? It's harder to start the object sliding than it is to keep it moving at a constant rate. That's because the amount of force that you have to push with to get it started moving is larger than Fs max. But the amount of force that you have to push to keep it moving is only the kinetic frictional force, F sub k. F sub k is always less than Fs max, so it's easier to keep the object moving than it is to start it moving. So, just something to kind of keep in mind. Let's imagine we come along and we push on this object with a force of, let's say, 10 newtons. What happens? To figure that out, we're going to draw a particular kind of diagram. Now, I've been doing this before, but I never mentioned it exactly what we were doing. We're going to draw a diagram and include all of the forces acting on the object. Whenever we do that, when we draw a diagram that includes all of the forces acting on our object, it is called a free body diagram. When we were doing kinematics problems, I always emphasized the importance of drawing a diagram to show how the object was moving, how was it accelerating, something like that. We're now switching our diagrams to free body diagrams because what we are interested in now is what are the forces that are acting on the object. At this point, for this problem, the question is, what's the acceleration of the object? Is it going to move? Is it not going to move? If it is moving, what's its acceleration? From that, we can always go back to the kinematic equations and figure out, well, where is it? What's its final velocity? How much time does it take? Blah, blah, blah. We already know how to do that. For these problems, we will assume once we get the acceleration, typically, we don't need to worry about it anymore. That's what the problem is going to ask for these problems for the most part. We're just looking for the acceleration, and we can assume once we've got that, we've got the problem solved. So, we're going to draw a free body diagram. We're going to include all of the forces. So, free body diagrams include all the forces. Remember, we always have to first think, what's the object of the problem? What's the physical body on which the forces are acting? Sometimes that is obvious, maybe sometimes not, but a very, very important question to think about ahead of time, or I should say in the beginning. What's the object that the forces are acting on? Well, it's this 15 kilogram body. So let's draw in the force that we just mentioned, the pushing force. Let's assume that we're pushing on it, and we'll push on it to the right with a force of 10 newtons. Given that, what's the acceleration? We can't just stick 10 newtons into Newton's law, because remember, F equals ma. What's that F? It's the net force. It's the total force. So we can't just stick any old force into it and figure out the acceleration. We have to find the net force acting on the object. What other forces are there? We know there's weight. What direction is the weight? Straight down. So there's a weight straight down. What's the magnitude of the weight? Weight equals mg. mg. M is 15 kilograms. We multiply by g. What do we get? 147 newtons. So 147 newtons. Let me actually redraw this over here. We've got a lot of numbers here. I don't want to make it too crowded. Let's just redraw the diagram over here. We've got our surface. We've got our mass. What forces are there? We've got a 10 Newton force pointing this way. We've got a 147 Newton force pointing down. These are not exactly to scale. This one would have to be 14.7 times longer than that one. So they're not to scale, so try and keep that in mind, that we need to think about the numbers rather than necessarily how long the vectors are. 147 newtons, that's the weight. What else? Well, anytime we have something resting on a surface, in general, we'll have a normal force. In this case, there are no other vertical forces, so we know we'll have a normal force that balances the weight, which is 147 newtons. There's going to be a frictional force. Is this frictional force going to be static or kinetic? In other words, is this object going to slide or not? Assuming that the mass started from rest before we started pushing on it with a 10 Newton force, the question is that 10 newtons larger than the maximum static frictional force or not? We are going to have some frictional force back this way, but we don't know how big it is. So let's look at Fs max. What is Fs max? Remember, Fs max is mu s times the normal force. Mu s in this case is 0.200. So 0.200 times the normal force. Well, the normal force we already figured out is 147 newtons times 147 newtons. We multiply that out, and what do we get? We get 29.4 newtons. 29.4. So, let me give you a second and think about this. Does the block slide or not? The object, let's just call it a block. Does the block slide or not? Well, the pushing force is 10 newtons. Fs max is 29.4 newtons. The frictional force is strong enough to overcome the pushing force. In other words, the pushing force is not strong enough to overcome the frictional force. So does the block slide? It does not. So what's the acceleration? The acceleration is 0. So for this problem, the block remains stationary with a 0 acceleration. What is the value of the frictional force? Keep in mind, the frictional force, the static frictional force, does not have to equal its maximum value. It's only going to be equal to as large as it needs to be in order to keep the object stationary. In other words, in this case, the static frictional force will be 10 newtons. It's only going to be as large as it has to be to balance the other force acting on it. So what's the net force acting on the block? We've got 147 newtons up, 147 newtons down, 0 net force in the y direction, assuming that we think about x and y this way. What's the net force in the x direction? 10 newtons to the right, in other words, 10 newtons in the positive x direction, 10 newtons in the negative x direction. What's the net force in the x direction? 0. 0 net force, 0 acceleration. The block does not move. Excellent. Let's imagine we've got a very, very similar situation, but rather than pushing on it with 10 newtons, let's imagine we now push on it with 100 newtons. 100 newtons. And I'll actually write it as 100.0. We'll see why in just a minute. Very good. Now what changes? What do we have to change here? Well, let's notice. If we were to start this from scratch, imagine that we hadn't done any of this work and we're starting it from the beginning. How do we know whether the block will slide or not? We have to compare our pushing force with the maximum static frictional force. We go through our calculation. The normal force is 147 newtons. 147 newtons. The weight is 147 newtons. The normal force is 147 newtons. We now have a pushing force of 100 newtons. We might write this as F sub P or F sub push is 100 newtons. Is that strong enough to overcome the maximum static frictional force? Well, we figure out Fs max, 29.4. Yes, it is. The pushing force, 100 newtons, is larger than Fs max. Let me just emphasize at this point, if you're actually taking my class and you have to take quizzes or exams and things like that, I will give you problems like this, and I will say almost with 100% certainty, you will see a similar problem to this, and I will ask you to explain your reasoning. To explain your reasoning as to whether the block slides or not, what you need to say is that F push is either greater than Fs max if it slides, or it's less than Fs max if it does not slide. And then it's a good thing to put the numbers in there. For example, F push is greater than Fs max. In other words, 100 newtons is greater than 29.4 newtons. Or, as in the first problem, 10 newtons is less than 29.4 newtons, to emphasize if it does not move. So I want to make sure that you understand why it slides or why it does not slide, and what forces you are actually comparing. And you've got to make sure that you are comparing the pushing force with Fs max. You're not comparing the normal force or the weight or anything like that. It's going to be the horizontal forces, the pushing force for this particular kind of problem with the Fs max. That will be what determines if the block slides or not. All right, very, very good. Let's continue. So in this case, what do we have? We have that, and I'll write this out. Because F push is greater than Fs max, in other words, 100 newtons is greater than 29.4 newtons, the block slides. So what? So the friction is kinetic. So the friction acting on the block is kinetic. If the block starts to slide, the friction acting on it is no longer static, it's kinetic. So over here, we need to put, this is the kinetic frictional force. What is the value of the kinetic frictional force? Well, F sub k is mu k times the normal force. Mu k is 0.150, excuse me, and the normal force is again 147 newtons. We multiply that out and we get that F sub k is 22.1 newtons. So this is 22.1 newtons. Very, very good. Let's look at, now in order to determine the acceleration, we have to figure out what's the net force. Let me just erase this part so we have a little more room. And again, let's keep in mind, I'm going to use this x and y coordinates. X horizontal to positive to the right, y vertical positive up. Let's look at the net forces in the y direction. What are the net forces in the y direction? Well, we have the normal force pointing upward, so that's a positive 147 newtons. We have a y force, the weight, which is downward. Downward is negative, and so the weight gives us a minus 147 newtons, which gives us a net force of 0 in the y direction. If that must equal ma(y), the net force in the y direction equals m times the acceleration in the y direction, ay. That tells us ay is 0. There's no vertical acceleration. That's just a point that we'll come back to very, very often. If an object is not accelerating in a particular direction, we know the net force has to be 0 in that direction. Okay, what about in the x direction? What forces are acting in the x direction? Well, positive is this way. The pushing force is in the x direction. What's the x component of that? Well, it is completely in the x direction, so we've got a positive 100 newtons. But then we have a frictional force, the kinetic friction, that is acting in the negative x direction. So that's going to contribute a negative 22.1 newtons. So minus 22.1 newtons. And that's the net force in the x direction. Well, we subtract these, and what do we get? We get 77.9 newtons. That is the net force acting in the x direction. What must that equal? That must equal the mass times the acceleration in the x direction, max. So ax is equal to f sub x over m, which is 77.9. That's why I stuck that extra 0 in there and made that 4 sig figs, so that I could actually keep that first decimal point and keep the net force as 3 sig figs. Divided by the mass, which is 15 kilograms. Divide that out, and what do we get? We get an acceleration of 5.19 newtons divided by a kilogram, meters per second squared. Excellent. There we go. Well, that was quite a bit. I hope that made sense. There are some homework problems on my website for you to practice those. I hope you enjoyed that. I'll see you next time.